Hello, and welcome to the TI Precision Labs module discussing calibration techniques for RTD measurement systems. Previous Precision Labs modules discuss common error sources and calculating total error. This module focuses on removing that error through calibration. Topics covered in this presentation include a discussion on general calibration, identifying a process for removing initial errors through calibration, and how much error is removed by this initial calibration process. A follow-up presentation introduces a method to calibrate over temperature error. To begin, let's discuss how the error estimation techniques introduced in previous Precision Labs modules affects the system transfer function. Under ideal conditions, an RTD measurement system has no error. This is represented by the horizontal green line in the plot on the left. An error-free system yields the green transfer function shown on the right. This response is considered ideal because it is unaffected by DC error. However, a previous Precision Labs module discussing error estimation plotted the actual error of an example system. This response is given by the red line on the left. The red error plot on the left translates to the actual response on the right, also in red. Note how the error across the input voltage changes the slope and y-intercept of the actual response on the right, which corresponds to the gain error and offset error respectively. Also note that to keep the analysis simple, we assume the actual response is linear. This assumption is valid because linearity errors are typically a small percentage of the total error, so excluding them from this analysis will not significantly impact the results. Refer to the previous Precision Labs module on calculating error in RTD measurement systems for more information. Next, let's discover what happens when we try to use this example system to measure some unknown input. On the left are the same ideal and actual transfer functions shown on the previous slide. When we apply an unknown input signal, RTD ideal, to the system, the generated ADC output is code ideal, as shown. Using the green equation on the right, we can determine that this ADC code corresponds to the RTD resistance given by RTD ideal. We can then use a lookup table or polynomial to accurately determine the temperature from that resistance. When we apply the same unknown input signal to the system in red, the ADC output is given as code actual. Since the behavior of the actual system transfer function is unknown at this point, we assume it follows the green ideal response. However, it is clear that code actual and code ideal are not equal. As a result, we can use the red equation on the top right to determine that code actual corresponds to RTD calculated, which is very different from RTD ideal. When we use a lookup table or polynomial to correlate RTD calculated to a temperature, our final result would be completely wrong when compared to the temperature that corresponds to RTD ideal. Calibration is therefore necessary to understand the behavior of the actual response so we can accurately determine the RTD temperature from the measured resistance. The next slide discusses which errors can be removed by calibration. The errors in this table come from an example introduced in a previous Precision Labs module discussing how to estimate the total error for RTD measurement systems. This table groups the different ADC and reference resistor error sources into initial errors in purple, over temperature errors in light blue, and total errors in brown. In the example, these errors were calculated with respect to the maximum RTD resistance, which was 194.1 ohms, and used the ADS124SO8 as the ADC. The ADS124SO8 is a 24-bit 13-channel Delta Sigma ADC with an integrated amplifier and current sources that is commonly used for RTD measurements. Let's make some general comments about which of the errors shown in this table can be removed by calibration. As mentioned on the previous slide, linearity error is not removed by the standard calibration process. This is acceptable because the linearity error is typically small, which is the case in this example. A multi-point calibration can be performed to remove linearity, but this is a very time-intensive, cost-prohibitive process. ADC noise is inherent to the device and cannot be removed by calibration. Averaging multiple samples can help reduce noise in some cases. Please see the Precision Lab series on ADC noise for more information about noise mitigation techniques. The remaining offset and gain error sources can be reduced by the signal chain process, though only to the level of the signal chain noise. The orange boxes indicate those errors that can be reduced by the initial calibration process, while the darker blue box indicate those errors that can be reduced by an over-temperature calibration. Over-temperature calibration will be discussed in a subsequent Precision Labs module. The next slide steps through a generic calibration procedure that can remove initial offset and gain errors. Shown on the left are the ideal and actual transfer functions introduced on the first slide in this presentation. We determined that the actual response has both offset and gain errors, which we can remove by calibration. The first step in the initial error calibration procedure is to remove the offset. As shown in the top right, the offset calibration involves shorting the ADC differential inputs together, typically to a mid-supply voltage. This helps keep the input voltage at the center of the PGA common mode range. Then, the measured output code corresponds to the combined offset of the PGA and the ADC. Averaging multiple conversions can help reduce noise in the offset voltage measurement. Finally, the offset voltage is subtracted from each subsequent measurement. Performing this action shifts the actual response in red down toward the ideal response in green. Each response still has a different slope, but both now have the same y-intercept. After offset calibration is complete, perform a gain calibration by applying a high-precision, near full-scale input to the system. Typically, a signal that is 95% of full scale is sufficient. Then, the measured output code corresponds to a scaling factor equal to the slope of the combined gain error of the PGA and the ADC. It is possible to calibrate the VREF gain error with this same measurement, though this requires an additional higher precision voltage reference compared to the VREF being calibrated. Calibrating the VREF error is not shown in the image on the bottom right. Averaging multiple conversions can help reduce noise in the gain error measurement. Finally, each subsequent measurement is multiplied by the scaling factor derived from this process. Performing this action rotates the actual response in red toward the ideal response in green. Now, both responses have the same slope and y-intercept, and the system is calibrated. While this method works well for general data acquisition systems, measuring an RTD creates distinct challenges that requires this process to be modified. As mentioned on the previous slide, the generic RTD measurement system, shown on the right, has several unique features that make standard offset and gain calibration less effective. First, the RTD output is always greater than 0 volts, so shorting the inputs for an offset calibration is not relevant for an RTD measurement. Second, an RTD measurement system uses a ratio metric reference, where RREF is often the largest source of error. Calibrating a ratio metric reference would require an additional higher precision voltage reference to be able to calibrate the RREF error. Moreover, RREF must be biased by an IDAC to generate the ADC reference voltage. This bias path flows through RRTD, making it impractical to also apply a full-scale signal from a precision source. Ultimately, a better way to calibrate an RTD measurement system is to use precision resistors to mimic the behavior of a real RTD. This enables us to determine the shape of the actual system transfer function strictly within the RTD measurement range, providing more accurate results. The next slide introduces the initial error calibration process for RTD measurement systems. The goal of the RTD initial error calibration process is the same as the standard gain and offset calibration procedure. The system has an unknown transfer function similar to the one shown on the left, and we are trying to determine how the measured resistance maps to the ADC output. In this case, however, we only care about a limited subset of the actual response that corresponds to the RTD measurement range. Therefore, the first step in the process is to identify the RTD measurement range of the system for a specific RTD type. For example, the system needs to measure a PT100 from -50 to 250 degrees Celsius. Importantly, this process only works for this specific set of conditions. If different RTD types need to be measured or the temperature range changes, the calibration process needs to be repeated. Next, choose two precision resistors to represent the extremes of the RTD curve. These resistors should be very high accuracy and very low drift, because the calibrated accuracy cannot be better than the accuracy of these resistors. In other words, if you choose 1% calibration resistors, the best calibrated accuracy you could achieve is 1%. Then, connect each resistor to the RTD measurement system as though it were a real RTD, bias it with the ADC IDAC, and take a measurement. Averaging multiple conversions can help reduce any noise in the measurement. Finally, correlate the averaged, measured value from each calibration resistor with the ideal resistance value from a lookup table or polynomial. This maps the relevant portion of the previously unknown system transfer function, including errors, to the known RTD curve. The next few slides step through an example. For this example, let's calibrate a PT100 that has an alpha value of 385. The temperature versus resistance curve for this RTD is plotted on the left, and is derived from a lookup table or calculated using a polynomial. Note that while this simplified calibration process assumes the system transfer function is linear, the RTD response can be nonlinear and calibration will still work. Let's identify the RTD measurement range. This example will use the same system parameters we defined for the examples in the error sources and error estimation Precision Labs modules. These parameters are shown in the table on the right and include a temperature range from -50 to 250 degrees Celsius, which corresponds to an RTD resistance range of 80.31 to 194.1 ohms respectively. The relevant portion of the RTD curve is denoted by the gray dotted lines on the plot on the left. Though not shown on this slide, we will also select the ADS124SO8 as the ADC in this example. Next, we need to choose two precision resistors near the extremes of the RTD curve. We will refer to these resistors as RCal low and RCal high. Note that the actual resistance of these components does not need to cover the entire measurement range, because we know the response of the RTD curve. Instead, it is recommended to select the closest standard resistance values because these components are easier to find and therefore more cost-effective. Two possible values for the calibration resistors that can be used in this example are highlighted in yellow on the right. Let's move on to Step 3. Step 3 requires us to connect each resistor to the RTD measurement system as though it were a real RTD, bias it with the ADC IDAC, and take a measurement. The measurement system for RCal high is shown in the top right. The ADC code for this measurement is given as code cal high, which is highlighted in orange. Note that averaging multiple conversions can help reduce any noise in the measurement. Next, replace RCal high with RCal low. The measurement system for RCal low is shown in the bottom right. The ADC output code for this measurement is given as code cal low, which is highlighted in blue. Finally, we are now able to map the ADC output to the RTD curve. This slide shows the RTD curve on the left and the system transfer function on the right. Our measured values, code cal high and code cal low, allow us to map the RTD curve to the system transfer function, including all errors as shown. Now, we know which segment of the ADC code range corresponds to the RTD curve. This allows us to accurately determine the value of any measured RTD resistance using these ADC codes and their corresponding resistance values. To determine the value of any arbitrary measured RTD resistance after calibration, we need to determine the equation for the transfer function within our calibrated range. This requires the general equation for a line, which is the first formula shown on the right. Next, we can replace the variables rcal low and rcal high with their values in this example. These are 83.5 ohms and 193 ohms respectively. Because this is an arbitrary example, we need to choose values for the calibrated ADC codes. In a real system, however, these values would be measured and output by the ADC. In this example, let's choose code cal low to be 2,465,113 and code cal high to be 5,512,354, both in decimal. Now, we can calculate the slope of the transfer function using the second equation on the right. Entering R1, R2, C1, and C2 into the equation yields a slope of 3.59 times 10 to the negative fifth ohms per code. With the slope calculated, determine the y-intercept by applying either resistance code pair to the equation for a line. R2 and C2 are used in this example, which results in a y-intercept of negative 5.08 codes. Finally, we can derive an equation for any arbitrary measured resistance, Rmes. If we assume that the unknown resistance, Rmes, yields a ADC output code of 3,496,174 in decimal, we can then calculate that Rmes is 120.55 ohms. Now, let's convert this to a temperature. For this example, let's convert the measured resistance to temperature using a lookup table similar to the one shown on the left. As described in a previous Precision Labs module that introduced RTDs, a lookup table is easier to use compared to a polynomial because it is computationally simple. After locating the resistance value in the table, use the temperature values on the left and at the top of the table to determine the temperature. If the exact value is not included in the table, use linear interpolation to calculate the corresponding temperature. In this example, the measured ADC code of 3,496,174 in decimal corresponds to a measured resistance of 120.55 ohms at a calibrated temperature of 53 degrees Celsius. That completes the initial error calibration process. Let's now consider how this process affects the error sources introduced at the beginning of this presentation. The error table on the left was introduced earlier in this presentation, where the errors are calculated at the maximum RTD input resistance, RTD max. The plot on the right graphs these errors across the entire RTD resistance range used in this example, which was from 80 ohms to 195 ohms. After completing the initial calibration, the offset, gain, and RF errors can be reduced to the level of the noise as shown. The purple plot on the right reduces to effectively 0 microvolts of error at any measured RTD resistance. The total error then just becomes the over temperature error, as shown in the table on the left, and the brown plot on the right. If further error reduction is necessary, calibrate across temperature. This topic is discussed in a subsequent Precision Labs module. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content. Question 1. Which of the following errors is not removed by the calibration process described in this presentation? The correct answer is A, nonlinearity. Question 2. What is typically the largest error source in an RTD temperature measurement system? The correct answer is C, tolerance in the external resistor.